Okay, so in the next few videos, we're going to look at how computers are actually able to represent and understand everything in binary. Okay, so we've talked about machine code and how everything has to be ones and zeros in machine code, and that computers can only understand ones and zeros. And that's a little bit kind of hard to wrap your brain around, how everything could be ones and zeros. So that's what we're going to look at. So if you think about it, there's different types of information that computers have to be able to generate and use. Okay, so first of all, computers have to be able to represent and work with numbers. So that might be integer numbers, that could be decimal numbers, but they have to be able to work with numbers because they need to be able to do math, like add and subtract, multiply, divide, that kind of thing. So they have to be able to represent numbers and work with numbers. They also need to be able to work with things that are like letters or characters from the alphabet. But there's also other things that aren't actually letters, but are similar to letters. So things like punctuations, commas, semicolons, basically anything that you can type on a keyboard. Kind of consider that as a letter kind of thing. So we usually, in Python and other programming languages, we call those characters actually. Okay, so this kind of character is, they're not numbers, they're something different. So these characters, the computer has to be able to represent and work with those. And then, in order for a computer to actually do anything, it has to be able to work on instructions. So instructions like things like add two things together, or subtract two things, or compare two things, or so different kinds of instructions that the computer has, so it's actually doing something. Like if all you have is numbers and letters, but you aren't actually doing anything, then your computer is no good. Okay, and so we're going to look at these three different kinds of things: numbers, characters, and instructions, and how each of those can actually be turned into binary, things that use only ones and zeros. Okay, so the first thing we'll look at are numbers. Okay, so in order to understand how computers represent numbers, we need to kind of look at what a positional number system is. So whether you studied this before or not, we use a positional number system. And in particular, we use decimal numbers. So if you see a 2 followed by a 5 followed by a 3, we all know what that means. What does it mean? Well, we would say that the 3 is in the ones place. So that's the ones place. And the 5 is in the tens place. And the 2 is in the hundreds place. And so what this number means is I have 2 sort of with a weight of 100. So that 2 actually represents 2 100ths, or 2 times 10 squared. Okay. The 5 is in the tens place. It has a weight of 10. And so the value of the 5 is 5 times 10 to the first. And the 3 is in the ones place. So the weight of that 3 is, there's 3 ones. So that would be 3 times, and I'm going to write 1 as 10 to the 0. And then I would take these three things, values, and add them up, and that's what 253 means. Okay, it's 2 hundreds, 5 tens, and 3 ones. Okay, and so we call our number system the decimal system because it uses base 10. So if you look at like this root, this word comes from Latin for 10. So if the metric system, you see deca, deca, all those kind of, any prefix or root there with a DEC in it has to do with the number 10. Okay, and so we have a base 10 number system, and because it's base 10, there are 10 different symbols that we use, 0 through 9. So notice that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 symbols. And then it's a positional number system because the position of these symbols determines its value. So the position determines the weight. Okay, so we've got a 10 to the 0 place, a 10 to the 1 place, a 10 squared place, and so on and so forth. Okay, well, we can take those same concepts from our decimal number system and we can translate those into base 2 and just use those same concepts. So the binary number system, so that should speak the number 2 to you like a bicycle, right? So the binary number system uses a base of 2. And so here in base 10, we had 10 different symbols. In base 2, we'll only have 2 different symbols, 0 and 1. Okay, and then it's a positional number system, just like our decimal system that we know. And so the position of the symbol determines its weight. Okay, now here, the weight had a base of 10. So notice this was the base. The base of that exponent was 10. Now in a base 2, the base of our exponents will be 2. So here we have a base of 2. So instead of having a ones place and a tens place and a hundreds place, we'll have a 2 to the 0 or ones place, a 2 to the 1, a twos place, a 2 squared, a fours place. Okay, but the numbers work just the same way as base 10. Okay. So both the decimal system that we are used to and that we use and we're very familiar with and the binary system are positional number systems because they have, notice, these same categories. They have whatever the base is, they have that many different symbols, and then they use a position to base its weight or place value on. Okay, so let's do a little bit of practice and think about how the binary number system works. So let's say we have these binary numbers and we want to say, okay, well, this is 1001, but this isn't a base 2 or a binary system. So what would that be equivalent to in what we know, the base 10 system? Well, this, if you think about it, this is the 2 to the 0 place. This is the 2 to the first place. This is the 2 squared place. And this is the 2 cubed place. So if we want to look at the value of this number, it would be the symbol here, 1, times its weight or its place value, its position. So it has a weight of 2 to the 3rd. Okay, and then we would add on the next symbol, 0, and it's got a weight of 2 squared. And then the next symbol is a 0. It's got a weight of 2 to the 1st. And the last symbol is 1, and it's got a weight of 2 to the 0. Okay, so 1 times 2 cubed is 8. 0 times 2 squared is 0. 0 times 2 to the 1st is 0. And then 1 times 2 to the 0 is 1. So if we added those all up, we would get 9. Okay, so in base 9, in base 10, the number is 9. In base 2, that would be written as 1001. So we think of this as being the number 9. The computer can only understand it as 1001. Now, if we were looking at it, we would call it 9 because that's what we're familiar with. Now, the way that we can write this is we would write 1001 in base 2 is equal to 9 in base 10. So if I use this little subscript here, that'll just indicate what base I'm using. Okay, so in the base 2, or a binary number, 1001 would be the same thing as 9 in the decimal system. Okay, let's try another one. Okay, so notice this is the 2 to the 0 place. This is the 2 to the 1 place. 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, and 2 to the 6th place. Okay, so one thing that you'll notice from the previous one, we were just adding 0 anytime there was a 0. Okay, so if I were writing this out, and especially if I have a lot of digits, I probably don't want to include all of the zeros. I only need to include the ones where I have a 1. So I'm going to have a 1 times 2 to the 6th, which will be 2 to the 6th. And then I'll have a 1 times 2 to the 5th. and I'll have a 0 times 2 to the 4th, so don't bother with that one. I'll have a 1 times 2 to the 3rd, so I need to put a 2 to the 3rd in. I'll have a 1 times 2 squared, so I'll put 2 squared in. I won't have any 2 to the 1st, so I won't bother putting that one in. And then I'll have a 1 times 2 to the 0. Okay. And so that's just a little bit shorter way of writing out what the value will be. Okay, and so 2 to the 0 is 1, and 2 squared is 4, 2 cubed is 8, 2 to the 5th is 32, and 2 to the 6th is 64. So we would just have to add all of those up. Let's see, this would be 40, so that would be 104, 105, 113. Hopefully I did that correctly. Oops, I already added on the 8. That didn't seem right to me. So this was 40, that's 104, 108, 109. I thought there was something wrong about that. All right, so that's actually 109. Okay, and so the way we could write that is 1, 1, 0, 1, 1, 0, 1 in base 2 is the same thing as 109 in base 10. Okay, one last one. Okay, so this is the 2 to the 0 place. We don't have that one, so let's not even bother to write that down. But we do have a 2 to the 1st, and that would be squared cubed to the 4th. We have a 2 to the 4th, 4, 5, 6, 7, 8. That will be a 2 to the 8th. Okay, so the only ones we really need to add up are the 2 to the 8th, the 2 to the 4th, and the 2 to the 1st. Okay, 2 to the 1st is 2, 2 to the 4th is 16, and 2 to the 8th is 256. Okay, and so let's see, 18 added onto that would be 274. Okay. And so that means we have 1, 0, 0, 0, 1, 0, 0, 1, 0. Base 2 is the same thing as 274 in base 10. Okay. So that gives you an idea of if the computer sees this, it's really thinking of this number. That's the number that is being represented there. Okay. So notice I put here, this is binary numbers as positive integers. Okay, all of these were integers. But what if I wanted to represent some kind of a rational number, like 234.352? Okay, now none of these things back here had decimal places in them, and so we need to think about what you would do if you wanted to have a decimal number. So for instance, what would 1011.101 in binary mean? Okay, well, first of all, let's think about what it means in decimal. And then if we can understand how it works in decimal, it's pretty easy to just take our thinking and transfer it into a different base. So if here is our decimal point, this is the 10 to the 0 place. This is the 10 to the 1st place. This is the 10 squared place. And if we go the other way from the decimal point, this is the 10 to the -1 place. Or the 10th place, right? This is the 10 to the -2 place, or the 100th place. This is the 10 to the -3 place, or a 10 or the 1000th place. Okay, and so if we were to write out this number in its form, this would be 2 times 10 squared plus 3 times 10 to the 1st plus 4 times 10 to the 0 plus, and we just keep going with that same kind of idea. The 3, okay, would be times 10 to the -1. The 5, its weight is 10 to the -2, and the 2 is times 10 to the -3. Okay, that's how we would just, that's what the value of that sequence of symbols means. Okay. And so we just need to take that same kind of thinking and apply it to a different base, their base 2. So one thing to note that in decimal numbers, we call the little point, the dot there, a decimal point. But in base 2, we're not in the decimal system, so we should call it a decimal point. We would actually call it a binary point. Okay, so I will try to call it a binary point. Okay, so let's say we had 1011.101. Okay, well this just like we did here, we start at the decimal point, here we start at the binary point, and we'll label our place values. So as we know, this is going to be the base of 2 to the 0. This will be a base of 2 to the first. This will be 2 squared, and this will be 2 cubed. And just like we had exponents going, you know, down from 0 on the other side, so -1, -2, -3, same thing will happen here. So this will be a 2 to the -1, this will be a 2 to the -2, and this will be a 2 to the -3. So if I wanted to figure out what this number was, well, I could just expand it. So I have 1, I have a 2 cubed, one of those. I don't have any 2 squareds, but I do have a 2 to the first. I have a 2 to the 0th power. I have 1, 2 to the -1. I don't have any 2 to the -2s, but I have 1, 2 to the -3s. Okay, and so that would tell us what the number was. So let's figure that out. 2 to the 3rd is 8. 2 to the first is 2, 2 to the 0 is 1, 2 to the -1 is a half, and 2 to the -3 is an eighth. Okay, so if we add these all up, we're going to get 10, 11, and then 11 and 5/8. That would be as a rational number if we wanted it as a decimal number with a decimal point. Let's see here, 5/8 is 0.625, so that would be 11.625. Okay, and so we could write this as 1011.101 in base 2 is equal to 11.625 in base 10. Okay. What you might want to do is pause the video and try this one on your own, and then just fast forward to the answer, see if you get it. If you do, then you can just go on. If not, then you might want to rewind it and see how I figured it out. But that's a good way to test yourself and see if you understand the concept. Okay, so let's label the place values. This is going to be a 2 to the 0. That'll be 2 to the 1. This will be 2 squared. We don't have to bother writing that one in since it's 0. This will be a -1. This will be a -2. We have one of those, so I should write the 2 to the -2. And this will be a 2 to the -3, -4, and -5. All right, so this is going to be 2 squared plus 2 to the 0 plus 2 to the -2 plus 2 to the -3 plus 2 to the -5. Okay, probably don't want to do that all in fractions, so we'll put this up here. So we have 2 squared, we add on 2 to the 0, and add on 2 to the -2, add on 2 to the -3, and add on 2 to the -5. And this is what we get. We get 5.40625. Okay, so if we wanted to use this same notation, we would say that 101.01101 in base 2 is the same thing as 5.40625 in base 10. Okay. All right, so that shows us what the binary numbers mean. But we would also now like to be able to convert the other way. So far, all we've looked at is this is what the number is in binary. What is the equivalent in decimal? But let's say I gave you this decimal number. How would you convert it into binary? So we're going to start with just positive integers and convert those to binary. Okay. So the number 5, you can think about, like if I were just to draw some little slots. I've got a 2 to the 0 place, I've got a 2 to the first place, I've got a 2 squared place, a 2 cubed place, etc., etc., etc. So thinking about this, 2 to the 0 is really 1, 2 to the first is 2, 2 squared is 4, 2 to the cube, 2 cubed is 8. Okay, so I really have a 1's place, a 2's place, a 4's place, an 8's place, and on it would go. A 16th's place, a 32's place, and so forth. Okay, well, I'm obviously not going to have any 8's to make the number 5. I don't need to include this one. I would just have 4, which is less than 5 and down. And I really just kind of ask myself, all right, which of these places would I have to include to get the number 5? Okay, well, if I had a 4 and a 1, that would add up to 5. So I need one of these and one of these, and I don't need any of those. And that would give me 5. And so 1, 0, 1 in binary is the same thing as 5 in base 10. So you can kind of just reason it out by knowing the place values. Okay, now that gets a little bit more complicated, as numbers get bigger. So let's go ahead and go through that process with this one, and then I'll show you a better way to do it, because you're obviously not going to want to do that for 135. But let's, kind of follow the same process. All right, I have a 2 to the 0, that's the 1's place. I have a 2 to the 1, that's the 2's place. And then I have a 4's place. I have an 8's place, I have a 16's place, and next I would have a 32, but 32 is bigger than that. So obviously anything bigger than that, I'm not going to use those to add them up to make 23. So we only need to look at these places. Okay, how would I get 23? All right, well, 16 and 8 would be 24. That's too big. So I must have a 16 and a 4. That would be 20. And to get the other 3, I need 2 and 1. Okay, so 16 plus 4 plus 2 plus 1, that's 23. I didn't use the 8. Okay. All right. Now, that might take you a while with the 87 and the 135. Like, we probably don't want to go through that process of kind of trying to just like reason it out. So let me show you a method that you can use to quickly determine what it is. So I'm going to take the number 23, and notice I'm writing it low down here. Okay, and I'm going to take 23 and I'm going to divide it by 2. So 23 divided by 2 would be 11, and then with a remainder of 1. And I'm going to write my remainder over here. So all the remainders I'm going to write over here. Okay, and then I'm just going to do that again. So I'm going to take this 11 that I had and I'm going to divide it by 2. Okay, well, 2 goes in there 5 times with a remainder of 1. Again, I'm going to write my remainder over here. And I'm going to do it again. 2 goes into 5 twice with a remainder of 1. And then 2 goes into 2 once with a remainder of 0. And then 2 goes into 0 0 times with a remainder of 1. Okay, and at this point, if I kept doing it, I would say 2 goes into their 0th, remainder of 0. 2 goes into their 0th, remainder of 0. So I would just have a whole infinite number of zeros going up this way. So those aren't important. As soon as you get a 0 here, stop. Okay, and then if you look at the numbers that I have right here as my remainders, and you compare them to the numbers that I have written up here, hopefully you should see that they're very similar, right? So if I just to read this down, you will see that this 1, 0, 1, 1, 1 is the binary representation of 23. So I can get that binary representation by just this repeated division by 2 process. Okay, so let's try that with the number 87. Okay, I'm going to take number 87, and I'm going to divide that by 2. 2 goes into 87 43 times with a remainder of 1. And then 2 goes into 43 21 times with a remainder of 1. 2 goes into 21 10 times with a remainder of 1. 2 goes into 10 5 times with a remainder of 0. 2 goes into 5 twice with a remainder of 1. 2 goes into 2 once with a remainder of 0. And then I'll call it efficient. Maybe it's lazy efficient. I don't know what it is. But once I get to a 1, I usually just start there. I know that if I go 2, it's going to go in there 0, and I'm going to write my 1. If there's a 1 here, it's going to end up being the remainder. So I just kind of, if I get to a 1, just read it down this way rather than rewriting it. Okay. So 87 is going to be 1, 0, 1, 0, 1, 1, 1 in base 2. Okay. Now, this again would be a great time for you to try 135 to convert it. Just stop the video, do it on your own, fast forward, and see what I get. If you get the same thing as I did, great. You can just go on. If you're not, then you can rewind it and see where you might have gone wrong. Okay, 135, divide it by 2. All right, so it's going to go in there, what, 67 times with a remainder of 1. And then 2 will go into 67, 33 times with a remainder of 1. And 2 will go into 33, 16 times with a remainder of 1. And then 2 goes into 16 8 times with no remainder. Goes into 8 4 times with no remainder. Goes into 4 twice with no remainder. Goes into 2 once with no remainder. And now that I see that I have a number less than 2, I can just stop and use that. And okay, and I'll read it down this way. And so I get 1, and then 1, 2, 3, 4 zeros, and then 1, 1, 1. And that's what it is in base 2. Okay. All right, so that is the process for converting decimal numbers into binary, at least decimal integers into binary. Okay, but now we have the question of how you would do it with rational numbers that have decimal points in them. Okay, so let's start again and just kind of intuitively go through this one. So we have 3.75. If I write that as a fraction, that would be 3 3/4, right? So if I think about my so if I write my binary point here, I've got the 1's place, the 2's place. If I go out again, the 4's place, well, this number is less than 4, so there can't be a 4's place. I don't have to worry about that. And then I go to the other direction, I have the 1/2 place, and I have the 1/4 place, and then if I kept going, the 1/8 place, and so on and so forth. So to make the whole number 3, I would need a 2 and a 1. And to make the fraction 3/4, well, 1/2 plus 1/4 is 3/4. So I need those ones. And then that's it. I don't need anything out here. So again, I could put trailing zeros if I wanted to, but that's just like in decimal numbers. I usually cut off the trailing zeros. In binary, I'll do that as well. So this would just be 1.11 base 2. So that's what that would be in binary. Okay. Let's try that again with this one. So for the 6, we would want to have our binary point. There's a 1's place, a 2's place. Okay, this is bigger than 4, so a 4's place, but we wouldn't want to go out to an 8's place because that's bigger than 6. And then there's a 1/2 place, a 1/4 place, and a 1/8 place. So if you rewrite this as a fraction, this is 6 1/8. Okay. So to get the 6, we need a 4 and a 2. And to get the 8th, we just need an 8th. And we didn't need any of the rest of this stuff. Okay. Now, as you see, as the decimals get more and more complicated, you probably don't know what this is as a fraction, and you might, even if you did know what it was as a fraction, you might have trouble figuring out what fractions needed to be added up to get that. So when we start working with fractions and decimals, it's a little bit tricky. So let me show you the easier, quick trick way to do it, where you don't just have to kind of guess and check. Okay, so the whole number, the integer part of it, we'll do just like we did on this previous page. Okay, so the whole number part, the integer part, we already know how to convert. It's this decimal part. Okay, so I'm going to write down the 0.125, the decimal part. Okay, and I'll show you how to convert that. So I'm going to take a line through my decimal point, and I'm going to draw it straight down. And so my decimal point is always going to be on this line. I just like to draw the line so you can see where the decimal point is so that you can keep everything lined up. And when we had a number that was larger than 1, we used repeated division to convert it into binary. If we have a number smaller than 1, so some kind of a fraction, we're going to use repeated multiplication to turn it into binary. Okay, so we're going to take this and we're going to multiply it by 2. So I'm going to get 0.250. Okay, so notice that point should be right on this line. And it's very important that I always put something in front of the decimal point here. Okay, so in this case, that's 0.25. And then I'm going to multiply by 2 again. So 0.25 times 2 is 0.5. And then I'll multiply that by 2 again. And 0.5 times 2 is 1.0. And as soon as I get a 0 here, I can stop. And now, once again, if you look at these and compare them to the things in our binary number, they're exactly the same, and you're going to read these down. And so 0, 0, 1. Okay. All right, so to figure out this one, we need to do the 12. So you can either do the repeated division, or 12 is probably small enough that you can say, okay, 12, that's 8 plus 4. So I need an 8's place and a 4's place. Okay, so the 12 part of it is you're going to have a 1, 2, 4, 8. You're going to have 8 plus 4. Okay, so 1, 1, 0, 0 is going to be our 12. And then the 0.6875, this one we're going to have to do our repeated multiplication. So when I multiply by 2, I'll get 10, carry the 1, 15, carry the 1, 17, carry the 1, and 13. So that'll be 1.3750. Okay, make sure that the decimal point is on this line. And then multiply by 2 again. I'll get 10, carry the 1, that's 15, carry the 1, and that will be 7. So that's 0.750. Make sure that you put something in front of there. So if there's a 0, you need to put it in there. Then multiply by 2 again. So that's 10, carry the 1, and 15. So that's 1.5. And then multiply by 2 again. 2 times 0.5 is 1.0. As soon as I see the 0, I can stop. Okay, and so what comes after the binary point, so let me rewrite this. I'm going to have 1, 1, 0, 0. That's the 12. And then I put my binary point, and then I'm going to read these down. So I'm going to have 1, 0, 1, 1. So that is equivalent, the binary equivalent of 12.6875 in decimal. All right. And now it would be a good idea for you to pause the video and try this one on your own and then check it with my answer. If you don't get it, then you can go back and review any part of my solution that you need to. Okay, first of all, we're going to do the 28, and that's a big enough number that we probably want to do our repeated division process. So 2 goes into 28 14 times with a remainder of 0. It goes into 14 7 times with a remainder of 0. It goes into 7 3 times with a remainder of 1, and to 3 once with a remainder of 1. Okay, so if we read this down, that will give us the part before the decimal point. So we're going to want to read this one down, or sorry, the binary point. All right, and then this, for the part that's less than 1, we're going to have to use our repeated multiplication. So when I multiply this by 2, I get 10, carry the 1, that's 15, carry the 1, that's 7, and 8, and then 16, so it's 1.6875. Okay, we've already seen the 6875, but we'll go through it again. Okay, so we're going to get 10 carry the 1, 15 carry the 1, that's 17 carry the 1, and 13, so 1.375 times 2, that's 10 carry the 1, that's 15 carry the 1, and that's 7. Don't forget your 0. Multiplied by 2, that's 1.5, and multiplied by 2, that's 1.0. Okay, and we'll read these down as well. So the integer part is going to be 1, 1, 1, 0, 0, and then we put our binary point, and then the part that's the fractional part is going to be a 1, 1, 0, 1, 1. So that's what it is in base 2. All right, so you should be able to convert decimal numbers into binary, whether they're positive integers or positive rational numbers, and you should be able to go the other direction and take a decimal, a binary number and convert it into decimal as well. So either direction. And next time we will look at how you can represent other kinds of information. So far we've just looked at numbers, but we still need to look at characters and we need to look at instructions. And we'll do those in future videos.